Greetings, colleagues. Today we're going to be talking about a different topic than we've been working through class so far, and that is fluids. And now we've gone through class so far and we've built up a great knowledge of how solid objects move, and now we're going to take that and kind of view it from a completely different perspective and use the principles that we've worked up in this class through the ideas of mechanics to apply them outside of a topic that we've really explored in a lot of detail. So this little lecture is going to go through a quick introduction to the idea of fluids, and we're going to explore the concepts of pressure and of buoyancy, and then finally we'll finish off with a little introduction to fluid flow. Since this represents a departure from what we've talked about before, the best place to begin is with a introduction with some vocabulary. So when I say a fluid, that can be, probably evokes a lot of kind of knowledge in your head about like, oh, I know what fluids are. And we get a little bit more formal with our definition here, and we describe these as substances that can flow. So they lack a strong intramolecular bonding forces so that the actual particles of the material will move with respect to each other, and then those materials can change their shape in response to stresses. So if we apply a stress, it's going to sort of change its shape as a result. Informally, we sort of think about this as terms of like fluids mean that a fluid just kind of takes the shape of whatever container that it's in. So the external forces kind of dictate what its shape. It has no internal forces that are kind of large scale and holding it together. More formally, we think about this as having a near zero shear modulus for this object, and similarly the Young's moduli of these are also close to zero. They can have large bulk moduli, but the shear and the Young's moduli of fluids are low, because if you press them, like give them a tensile compression, or you try to cause them to shear, they'll just move without much resistance. Fluids include both liquids and gases. And we think about gases as being relatively compressible, so they have lower values of a bulk modulus, and then they have very weak interparticle forces. Liquids are usually significantly more incompressible, so high bulk moduli, and they have very strong interparticle forces. So this is only a relative statement. We still view gases as largely incompressible under sort of subsonic conditions, and then we will, use that fact as we kind of go on through the, explore how air and stuff like that moves. Okay. Given that definition, we define some properties within fluids. The one that probably causes you comfort and warm feelings is the idea of a density. Here we mean a mass density versus a number density or a particle density. The mass density is the mass of fluid per unit volume. So we give it the Greek letter rho, and it has a mass over a volume, and I'll use capital V for my volumes here. Density is an intrinsic property of material, so you probably have somewhere in the back of your brain that the density of water is 1,000 kilograms per cubic meter. This changes with the temperatures of the objects and the different substances that you're looking at, but density is kind of an intrinsic property of the fluid. We also define pressure, and pressure is this idea that a fluid is exerting forces per every unit area within that fluid. So if we think about a fluid here, this sort of white area all around, and then we think about a little area here, like if we inserted a little like thin sheet of paper or something into the fluid, it would probably get wet. But after that, you would be able to measure forces on it. And then there's a force on both sides of that paper that is equal to the force divided by that area, the force per unit area, is the pressure. And it doesn't matter which way we orient that piece of paper, the force that we measure on both sides of it would be the same. And this is kind of important because, like, if we think about all the high pressure from the air here in the atmosphere, it's 100,000 newtons per square meter. And that's enough to, like, push over walls and blow out windows and all of that. And the only reason why none of those things happen is that there's forces on both sides that are pushing in towards that little area. So we think about that basically everywhere in the fluid, if you put in a two-dimensional area, there's going to be forces on both sides, and the force per unit area is the pressure. So this is what we mean by it's isotropic. It doesn't matter how we orient that surface or whatever, the forces are always going to be pressing in, and they're going to have the same magnitude at that location, irrespective of how the orientation. But a pressure can change throughout a fluid. The classic case is atmospheric pressure diminishes as you go up higher in the atmosphere. So that gives you a change in the pressure as you go farther up in the fluid. Okay, this pressure, we think about this in terms of the microphysics, which is what's happening to the particles. We think of a fluid as being comprised of a bunch of these tiny little particles. And if we stuck in a sample area here, our dA, and we thought about what would happen with a particle, like a gas atom, coming in and bouncing off of that surface and going upward. So if this were a real surface, like a wall on the gas, this particle would come in with a momentum P sub I, and then bounce out with a momentum P sub F. And so this is an elastic collision. It sort of bounces up there, but in changing its momentum, we get a change in momentum of the particle that is net upward. So it bounces straight up, perpendicular to the surface. And as a result, there's an impulse on the wall headed downward. And so all these particles are coming in and bouncing off of this surface in the actual surface or a physics surface, and changing its momentum here will cause it to exert an impulse on the boundary, and then that impulse changes the momentum of the particle. And you can actually go through and derive the perfect gas law from this microphysics if you know how the speeds of particles relate to their temperature. And that's something that we can do in second and third year physics pretty happily, where we describe all of these and eventually grind out PV equals NKT, because we use Stefan Boltzmann constant in physics and not R like the chemists use. But anyways, we just can do all of this from the microphysics here. And that's well within our physics understanding. It's a little less tractable in terms of interesting math, so we don't do it here, but it's the result of all of these particles bouncing off the walls that gives us the pressure inside of a fluid. But that fluid pressure is not necessarily the same everywhere. And we can start to explore the topics of pressure and fluids to start to ask questions about how do, for example, pressure change with depth. So if you have ever been in a swimming pool and you've dived down under the surface, you start to feel the effects of pressure really pretty quickly. So you get the pressure increases over atmospheric pressure very rapidly with depth. And we can actually figure that out knowing a bit about the physics of water or physics of any fluid here by kind of considering what happens to a imaginary volume inside of a fluid here. So we're thinking about a fluid and we want to measure what's happening to the forces on this kind of volume inside this sort of cylinder as that cylinder or that volume is measured at different locations within the fluid. And we make the contention that the pressure will be changing with depth, and we want to find out how that works. So we want to measure down some distance y, and we want to consider the forces that are at work there. So we're going to define the positive y direction to be downward here, and there's going to be some pressure at the surface of the fluid. That's the atmospheric pressure here. And as we measure downward, the forces on this object, there's going to be a pressure force from the top that's pushing down, and so we're going to call that P at Y, and that's pushing down. And then there's going to be a force on the bottom that's going to be pressing up from the pressure at Y plus dy, and we're going to say that that's equal to the pressure at Y plus some small change in the pressure dp. So these are going to be tiny little volumes because, yeah, there's going to be a small limit and then an integral coming up pretty quickly. And so those will be separated by some distance dy here. And there's going to be forces on all the other sides here, but we're going to assume that those all balance out and that it's in equilibrium, and because they're at the same height in the fluid, they're going to have the same magnitude from the conditions of isotropy. Okay, so from that, we have a free body diagram for this fluid that we have the force on it, which is the pressure times the area, is P of Y times the area. So that's the pressure on the top pushes down. The pressure on the bottom pushes up. So this is P plus, it's P of Y. P of Y plus dP times the area pushes up. And then there's also going to be a weight of this little fluid here because it subtends a little bit of volume inside of the fluid. And so it's going to have a mass times g, gravity that's going down. And we're going to assume that this is in a equilibrium so that we have P of Y plus dP times the area minus, I've defined, the mistake I've made is I've defined downward to go downward, to be positive. So the positive forces here are mg plus P of Y times the area, and then the upward forces is in the negative direction, and that whole thing is P of Y plus dP all times the area, and that's equal to 0. Now, from the material as a fluid, we know that the mass of the fluid, m, is equal to the density of the fluid times its volume. So mass density times the volume. And that volume is going to be equal to the area times the height of that little rectangle. So it's the surface area A, which is the top area here, and then the height. So it's basically the area times the height gives me the total volume, and then I can plug that value in here. So we get that this, so we'll take this and we'll plug this back into this top equation, and we will get that this is rho g a times the little height of the object plus P of Y times A, and then I'll expand out this next expression, minus P of Y times A plus A times dP. Minus A times dP. Minus A dP is equal to 0. Now, from here, those P of Y terms will cancel out. And from there, we can solve. We'll push the A dP over to the other side. So we get A times dP is equal to rho g A times dy. There's an area on both sides, which we will cancel out. And we are left with an equation that is yearning for an integration here. So we get that rho g dy is equal to dp. And we're going to integrate that from y equals 0 to some arbitrary height or depth in the fluid. And then we're going to go from our pressure at the surface, P naught, up to some pressure P. And just rho times G is going to be a constant here because we're going to assume that the fluid is incompressible. So we get rho G times y minus 0 is equal to p minus p naught, because integral of dp is just p evaluated from p minus p, from p naught to p is p minus p naught, and then we just say p naught, move the p naught to the other side, plus rho g y is equal to the pressure at a given depth, which is a nice little relationship. Let's highlight it. Good thing to know. Okay, so we can derive what the pressures are here and get what is called Pascal's law. So Pascal's law is the thing we just derived here, that the pressure increases as you go farther down in the into the fluid, and pressure is the surface. And if P naught increases, so let's take, I took a fluid and I actually then compressed the air at the top of it, so this pressure increases. It actually just shifts all the pressures inside the fluid up by the same linear amount. So if I increase it by 1,000 Pascal at the top, all the fluid pressures everywhere increase by a total of 1,000 Pascals. And this is kind of an interesting phenomenon that is expressed in terms of Pascal's law, which is that pressure applied to the enclosed fluid, so if I push down on the top of this fluid surface with like a plunger or something, it is transmitted, and this is what says undiminished, to every portion of the fluid and the walls of the containing vessel, which is just this statement that we made up here, that the pressure is whatever the initial pressure is plus rho gh, and only rho gh is the only thing that causes a difference of the pressure at a given depth to the surface pressure. So you can really just relate those two. And so if I push down on the fluid, then that leads to an increase of pressure throughout. And this is a deeply useful phenomenon that we engage with hydraulic systems. And it's a great mechanical advantage that it's a great way of obtaining mechanical advantage. So we often think about this in terms of like a connected fluid tank where there's two openings. One has an area of A1 and the other one has an area of A2 that is larger than A1. And if I push down on that A1 with some force here, this is going to lead to a pressure here that is going to, or this force is going to be met with some resistive pressure times that area. So basically P naught is the force over A1. And so I press down on that force here. And that force actually has to balance over here. If this isn't going to go anywhere, this F2 is going to have to balance P naught times A2. The pressure is going to be the same on both sides of the system, even though the areas are different. So if I push down with a little force on the little area, there's going to have to be a sort of a larger force pressing down on a larger area to keep this in equilibrium. Otherwise, the fluid's just going to rise up and overflow the tank or some other hilarious options here. And this allows us to engage in force magnification. So if I have a heavy weight over here and I push down a little bit on this fluid, that force is going to be magnified by the ratio of the area. So if A2 is larger than A1, it's going to be larger by that factor. And that's what happens in the cases of hydraulic pistons. So this is a little, piece of construction equipment. It's an excavator. And if you look at those excavators, they often have these long, complicated arms that are controlled by a piston here. And what this this yellow object right here is it's filled with a fluid, and it has a sort of a pump that goes down to the engine that pumps fluid into it. And this tiny little sort of pipe presses fluid into this piston. And so it exerts a force per unit area, or a pressure here. And then that pressure has to push on a larger sort of area to force this piston there. It forces the piston to kind of extend. And the nature of it is if you back off the pressure there, this fluid is going to be over pressure. It's going to push fluid back down the pipe here. And so then it's going to relax. So this thing this piston ends up being something that you can sort of push forces on, push fluid on, extend it, and then it will naturally relax back into its equilibrium condition and pull the system back. So it's a very nice kind of one-way spring, and two-way spring. So it sort of pushes forward and pulls back. And the reason for that is just mediated through this mechanical advantage through hydraulics. Another neat example for this is through the construction of barometers. So barometers are weather devices that measure changes in atmospheric pressure. They're essential for predicting local weather conditions. And the early barometers took advantage of this Pascal's law relationship. And what you would do is you take a glass vessel, this is called a Goethe's device, which is a glass vessel, and you basically seal it and make a closed chamber here at some atmospheric pressure. You don't know what it is, but it's, on a nice day, you made a Goethe device, and you fill it with fluid. And that fluid has a little spigot that is here, and it comes up, and there's an opening, and this top part here is open to the atmosphere, and it is experienced at the top of this fluid some current atmospheric pressure. And we know from the Pascal's relationship here that that current atmospheric pressure, and then I go down some depth h plus rho gy is equal to the pressure in this side of the container. And so I can figure out what my pressure in this side of the chamber is by kind of solving for it in terms of minus rho gy. And here the fluid is above the level that's inside the chamber. So that means, as I've defined it, this y is greater than 0. So y is greater than 0 here. And that means that the atmospheric pressure minus the original pressure is less than 0, or that the current atmospheric pressure is less than the original atmospheric pressure when this device was changed. And so as the weather systems go through and the barometer or the atmospheric pressure changes, this fluid moves up and down. And we can just use that in terms of this Pascal's relationship to determine it. It's another kind of barometer is a mercury barometer. And here the idea is you take a sort of dish of mercury and you sort of suck some up into or you fill a tube with vacuum. I guess that's weird. You empty a tube of air so it becomes a vacuum, and then you stick it into this vessel of mercury and it sucks up the mercury into this fluid or into this tall column here against gravity. And then you can use Pascal's law here to say, okay, the pressure at the bottom down here, PATM, at this level of the surface is equal to the pressure at the top plus rho g times the depth of the fluid, which is the length of the column that goes down here. But since we created a vacuum at the top, that's basically 0 up here. And the atmospheric pressure is just the mass density of mercury times g times how far up this column the mercury travels. And so you'll often see in weather forecast units of pressure that are expressed in terms of millimeters of mercury. And that's just referring to this kind of atmospheric barometer here. We have since moved on into far more metrically useful quantities, but that is a good example for how this Pascal's law can be used. The next topic we want to work on is that of buoyancy. And the buoyancy is often expressed in terms of Archimedes' principle. You know, the Eureka person who, sat in the bath and figured out how to calculate the mass density of the king's golden crown or what have you. Archimedes' principle was what happens when an object is submersed into fluid, partially or completely submersed into fluid. That fluid exerts an upward force on the object equal to the weight of the displaced fluid. So I'm going to say force there because it's not a 4 on the object, it's a force. And so that force is equal to the weight of the displaced fluid. Okay, we can actually derive Archimedes' principle from the physics that we've developed so far if we think about putting an object into a fluid here. So we've stuck our green little object in the fluid, and again, it's going to be a rectangular prism, and we're going to orient it so that it has an area at the top and at the bottom here. So that's the area A, and there's a corresponding one underneath. And there's going to be a difference in pressure of the top relative to the bottom that results from this Pascal's law. And what we have is this is going to create a buoyancy force. So this buoyancy force, F sub B, is going to be equal to the difference in pressures. So it's going to be equal to the bottom pressure, which is going to be pressing upward, minus the top pressure that's pressing downward, all times the area of that object. And from the Pascal's law, we know that the pressure at the bottom here is going to be equal to the pressure at the top plus rho g y minus the pressure at the top, because y is going to be the height or the difference in the height of the object. And so that's all going to be times the area. And so this is going to be the p tops will end up canceling out. And then this is going to be equal to rho times g times the vertical height of the object, which I guess I'm calling y here, times the area. And if you'll notice that the y times the area here, that's the volume of the object, and the volume times the mass density is equal to the mass of the fluid. So this is m times g, where rho is the mass density of fluid, and the mass density of fluid, and then y times a is equal to the volume of the object. So then this is the mass of the fluid that is displaced, or what's pushed away from there. And notice that we are using rho, which is the mass density of the fluid, not the mass density of the object that's doing this, because the mass density of the fluid is what's controlling the difference of the pressure. So this all follows from the Pascal's law and the relationship that we derived earlier. All right, so from there, we can move onward to an example. And in this case, we have a precious carbon crystal that is lowered into a bath of water by a light thread. And that whole thing is sitting on a scale. So that's down here. It's measured on a scale. We'll come to why that's important in a slide. And what we want to do is if I drop this crystal, this diamond, into the water, I'd like to know what is the tension that's on the string right here. So notice, I'm just going to say before I put it in the water. So before it's in the water, we would have it suspended and we'd just have tension and we'd tension up and weight going down. And so that the tension would equal to the weight of the diamond, which is just equal to 0.050 kilograms times g, which is 10 meters per second squared, and that would give me 0.5 newtons. So that's before you stick it into the water. Once I stick it into the water, my free body diagram will change. And that free body diagram is going to start to look like there's a tension force, there will still be a weight that's pushing downward on this, and then there's going to be a buoyancy force that's pushing up on the whole system. And what we'd like to do is figure out what the buoyancy force of the diamond is. And we know that F sub B is going to be equal to the weight of the water that's displaced by the volume. So it's going to be the volume of the diamond times the mass density of water, rho H2O. So that's the mass of water that's displaced times G, and that's going to be pushing it upward from the sort of equivalent pressure. And note, I probably should have said on the previous slide, this is a weird shape, and then we have like the rectangular prism previously. What we do is we sort of describe each tiny little part of this as its own little rectangular prism, and so we decompose it. We had no constraints on what the actual size was previously, so we can make this is just a tiny bunch of little individual blocks, all of which sum to give your original object. So, calculus style, we would solve this in the limit, and then the law will hold in general. So with that digression out of the way, we'd like to then solve for the tension here. So we know that the tension is equal to the weight of the diamond, MB, G, minus the buoyancy force, FB, which is going to be M of the diamond times G minus V diamond times the density of water times G, and that's going to be the buoyancy force going up. And so then we can plug in the volume of the diamond, but the volume of the diamond, V diamond, is equal to the mass of the diamond over the density of diamond, which is actually given up there. So rho sub D is the mass density of diamond. So we get that this is equal to mdg minus md over rho d times g. And then we'll factor out an mdg. 1 minus rho, I forgot a rho H2O up here. Rho H2O over rho diamond. And I can plug in my numbers. So this is 0.050 kilograms times 10 meters per second squared times 1 minus 1,000 kilograms per meter cubed over 3,500 kilograms per meter cubed. And that whole thing is equal to 0.357 newtons. So that means that the tension of the spring just becomes 0.357 newtons. Okay. Great. So you'll notice that the ratio of the densities cropped up here. So a denser object would end up basically having its this higher density down here will end up reducing this 1 minus term, and so the tension will be closer to the original tension. So that's just a statement that basically you get a force upward that is determined by the density of water, and so the farther you are from it, the less of an effect that you will get. Okay. What I'd like to know now is what will happen to the reading on the scale. So let's say I have some volume of water in there. I'm not going to tell you what it is. I want to know how much it changes by when I dunk my diamond into the water. Will it change at all? Will it, what is overall the net value? So the way that we can think about this kind of two different ways. I think the easiest way to think about this is that we basically have a before case where we have a tension and we have the weight of the diamond as one set of forces that are suspending the diamond. And then we have the weight of the water, let's call it, mH2O times G, and then we have the normal force of the scale. So this is before we dunk those two things together. And so what happens here is the normal force of the scale, this is what's being measured. So remember, scales measure normal forces. Scale measures n. Okay. So when we stick this in here, we actually have to combine these two. And so if we consider this whole thing as a system right here, what we're going to do is when we stick the water in there, our free body diagram, you'll remember, changed to T, M, D, G, and then this tension force was reduced because there came to be a buoyancy force here. But overall, nothing in the system changes. So this tension force decreases, and then there's this buoyancy force upward. And so that buoyancy force must come from somewhere, and it's going to exert a downward equal and opposite sort of Newton third law force on the water here in the system. And then there's going to be a new normal force. And so that new normal force is going to increase relative to the original normal force. Basically, the water is having to contribute to forcing the diamond upward, reducing the tension, and in kind of the overall force budget of the system, that means that the scale is going to have to be pushing up on the water to balance out that buoyancy force. And what that means is that the normal force, so therefore, the new reading will increase by the amount that the tension decreased. That tension decreased. And so the tension decreased by the factor of rho H2O over rho diamond times M diamond times G, which is just the 1 minus, that's this term here. And that comes out to be 0.143 newtons, which was the 0.5 newtons minus the 0.357 newtons from the previous problem. So the scale will increase by 0.143 newtons. Okay. So that brings us to the end of kind of the ideas of buoyancy. There'll be some examples in the example video. But here, let's think about fluids and what happens when they move. So we've largely dealt with statics, fluid statics. We can also think about fluid dynamics. And I love fluid dynamics. It's one of my favorite corners of physics. And it's also one of the great unsolved problems in physics. It is very hard to kind of deal with fluids in their general realistic case. But here in this class, we can really simplify fluids to make some of our problems pretty tractable. And what we're going to do is we're going to work primarily with ideal fluids, and we're going to also work with ideal fluids. And those ideal fluids are going to be incompressible and inviscid. So incompressible means that their bulk modulus is basically huge, practically infinite. And so if I push pressures on them, their volumes aren't going to change. Their pressures can change, but they're not going to change their volumes here. For liquids, this is pretty good. We saw that the bulk modulus of water was somewhere in the tens of gigapascals. We saw like a 5% change in the previous video when we went from the surface of the ocean down to the bottom of the San Marianas Trench. And so that gives us like the basically pretty good assumption for liquids. For gases, it's actually also pretty good. I know in the kind of chemistry world, you often deal with pressure and PV and NKT and all that, but gases are pretty good if you're dealing with velocity of the fluid flow that are less than the sound speed, so much less than the sound speed. So it's a reasonable assumption, and this just means that the pressure forces inside there can kind of transmit changes quickly, and so the pressure will kind of balance out the forces inside the fluid faster, then you can kind of change the shape of the fluid. So that condition of if the fluid flow is less than the sound speed, then you'll probably get pretty close to incompressible physics. The other thing is no internal viscosities of the fluids. And this is the thing that is probably the biggest lie. If something is inviscid or has no viscous, it's basically what's called dry water. That means that stuff flows across without having any intraparticle interactions. And both gases and fluids have substantial viscosity in them. Even if it's relatively small, it plays a huge effect on the behavior of systems because of the way that the viscous terms enter into the force equations for fluids. They end up having this very kind of massive outsized effect, leading to phenomena like turbulence. Okay, so that's a sort of preface of fluid flow here. Let's dive into some vocabulary. So when we think about fluid flows, we're really going to be focusing on kind of smooth, steady flows. And if you have that kind of fluid flow, you can think about the trajectories of the particles in a moving fluid in terms of a flow line. And so this is kind of a bad illustration of flow lines. So a fluid flow can sort of pass through one area here along a set of flow lines, and these flow lines are kind of little trains of particles here. Flow lines don't cross typically in the nice flow that we're dealing with, so they sort of, all the particles kind of move one after another along these flow lines here. We also have this idea of streamlines, and that is the curve that is tangent to the velocity of the fluid particles. And flow lines and streamlines are not the same if the flow lines are changing over time. But we generally deal with the case of steady flow. And that's where the flow lines are kind of time stationary. They don't vary over time. And in that case, the flow lines are the streamlines. So the velocity is just pointing to where it's going, and there's no overall shift in the pattern of the fluid flow. If we think about kind of two areas here, we can imagine all of the flow lines that go through one area where the sort of the area that they end up later on is going to be bounded by some surface. And the flow lines are basically passing through one area, and then the ensemble of them pass through at a later area. And no fluid then crosses the walls of this tube because of our stipulation that the flow lines don't cross. And so we end up with a kind of nice, steady flow here that we'll often describe as a laminar flow, which means the flow is moving in layers. So they can move at different speeds in a fluid flow, but then there's no actual mixing between those layers. This stands in contrast with basically all the important fluid flow problems, which are turbulent flow problems. And there's no steady state patterns. There's no flow tubes. All of these kind of areas are constantly getting distorted and stretched out. The streamlines aren't equal to the flow lines. So turbulence is glorious and a wonderful mess, and we will get to that. But the framework that we build up here is helpful for understanding all of fluid dynamics. Well, with that as preface, let's think about what happens in a system that is moving along these flow lines. And we think about sort of a bunch of flow lines that pass through an area A in some little bit of time dt. And we often have we say that fluids are subject to the criterion of continuity, which is that mass that is entering into a region of steady flow, so coming in through the bottom of this surface, is going to be equal to the mass that leaves it in the same surface. So it's basically a one in, one out kind of model for every volume. And that's basically a statement that there isn't a creation or destruction of a fluid in its flow. In that case, we have a condition of continuity. And then we can just assert that the flow through this area here is going to be the same everywhere along the flow tube at a given time. So basically the amount of mass here, A1 times this little thickness here, is going to be a volume, and that's the velocity of the fluid flow times time. And that's going to be equal to the same kind of construction, area times V dt, later in time. And because those masses have to be equal inside those little volumes, then we have the relationship that A1 times V1 is equal to A2 times V2. So if the fluid tube is moving faster, its area has to shrink down here. This quantity, A times V, is called the volumetric flow rate through the tube. Okay, now we also can have the case that the density of the fluid can change. In that case, then the density times the area times V is going to be a constant over time. So that is, again, is asserting that the mass passing through a flow tube per unit time is always going to be a constant, because you're not building up or reducing mass inside of these flow tubes. And one case where you really end up seeing this a lot is in the case of basically when you're pouring a fluid. You can see this phenomenon at work. And here, I think about our precious Canadian maple syrup being poured out onto a table for some reason. And this wonderful artificial intelligence generated image knows that this is the fluid flow is thicker at the top than it is at the bottom. And this phenomenon is essentially a flow tube. All of the fluid flow passing through here, and here is going to be basically it's going to have the same volumetric flow rate through here, and there's no fluid going out of the flow tube. If we have at the top, we are going to say that up here we have a cross-sectional area of 0.05 centimeters squared of area through the flow tube at a point where its speed is 0.3 meters per second, then we want to know how thick is the flow tube at the bottom after it has fallen 10 centimeters here. So we have the relationship that the volumetric flow rate at the top is equal to volumetric flow rate at the bottom. We're going to assume that the density of our maple syrup doesn't change, so assume rho is a constant. And from here, we can figure what we need to do to figure out the area is clearly we have to find out what the velocity is at the bottom. But every particle that's in our flow tube is in approximate free fall, and so we have a kinematic expression for that. So we know that for free fall, I guess we have an evacuated kitchen table here, but no air resistance here. So for free fall, we have the case that the final velocity squared minus the initial velocity squared is equal to 2 times g times the height that it falls. So that's 1/over kinematic equations. And just from a constant acceleration moving downward, every particle is going to be subject to this. So that means that I can figure out what my final speed is. So I know that Vf squared is going to be Vi squared plus 2gh. And then so we get Vf squared is equal to Vi, then we get that Vf is equal to the square root of V1 squared, or Vi squared, plus 2gh, and then I can just plug in that Vi here is 0.3 meters per second, quantity squared, plus 2 times g, 10 meters per second squared, times the height that it falls down, which is 10 centimeters, 0.1 meters, there, and come out with this to be 1.44 meters per second. Then I can figure out what my A2 is as A1 times V1 over V2. And so that's 0.05 centimeters squared times V1, which was 0.3 meters per second. And then we divide by the new speed, which is 1.4 meters per second. And out comes our result that's at 0.01 centimeters squared. So that gives us our expression for how the fluid thins as it kind of free falls down there. Okay, so the last thing we want to talk about is how the principles of work and energy apply inside a fluid flow. And this leads to something that's called the Bernoulli equation. So Bernoulli equation applies to incompressible fluid flow with changing pressures. And what we think about this is we think about the work and energy done on a flow tube of material as that material moves through a vertical height y, basically anything with a potential energy here. And we want to think about the pressure sort of pushing on the bottom of the flow tube versus the pressure that's pushing on the top of the flow tube when we think about the work that is done by those pressure forces. And I argue that the work done at the bottom of the flow tube is going to be the pressure times the area of the cross-sectional area of the flow tube times the speed that the fluid flow is going through here times time. And so that's basically going to be the distance. So this is essentially force, pressure times area, times displacement, v dt, is going to describe how much work that is done on the fluid from a pressure pushing upward on it. So sort of forcing it along the flow tube. And travels along a flow tube up a little later, and we'll consider the top in a moment. The kinetic energy at the bottom of this flow here is going to be 1/2 mv squared. And we know that our expression for mass is the density times the volume. The volume of that flow tube is the area times the thickness of it, which is v dt, times v1 squared. Okay, so that gives me kinetic energy. And then the potential energy, measured from some arbitrary point y, is going to be mgh, which is the mass times the mass density times the volume times the acceleration due to gravity times whatever its gravitational coordinate is. Okay, so that's the energy at the bottom of the flow tube, and I can repeat the energy at the top of the flow tube. The work here we're going to treat as a negative work because it's working in the opposite direction of the flow tube. So we think about the pressures sort of pushing externally on the flow tube between point A and point B. The pressures are pushing inward in both directions. But in this case, the force is acting opposite the displacement. And so we get a negative work from that equation. The kinetic energy follows similarly, 1/2 mv squared, and the potential energy is mgh, where again, m we've written as the density times the density times the volume, which is AV times dt. Notice we've left the densities that are the same, and that comes from the incompressible nature of the fluid flow. Okay. So we can then apply the work-energy equation. So we have a change in gravitational energy plus the change in kinetic energy is the work that's done on the system. And then I just plug in my two corresponding parts. So this is the change in potential energy, change in kinetic energy, and then the work that's done on the system here as positive work minus negative or plus negative work, which is the positive work at the bottom and the negative work at the top. And you'll notice as we go through here, every one of these terms is going to carry with it an AV dt. So there's a dt in everything, and then there's an A2 and a V2. But because A2V2 is equal to A1V1 through the criterion of continuity, remember this is a flow tube, we've set it up, and we automatically get continuity, we can cancel out the A2s and the V2s. And so everything here is going to cancel out, and we get a nice little relationship that the density, G, difference in heights, plus 1/2 density, difference in velocity squared is the difference in pressures. And then we'll rearrange this so all of the top equations and bottom equations are on the top. So we get rho gy plus 1/2 rho v squared plus p at the top is equal to the same thing for the bottom. Or since these two are the same at the top and the bottom, Along one of these flow lines, we get the criterion that the density rho gy plus 1/2 rho v squared plus p is equal to a constant. We don't know what it is, but that constant always remains fixed. So this nice Bernoulli equation gives us the capstone here in Physics 144, which is that it gives us the opportunity to explain how planes fly. And what's happening in plane flight is air is flowing over the wing and is being subject to the Bernoulli equation. And so this sets up this nice, smooth, incompressible laminar flow over a wing. And this does a little numerical simulation of the particles here. The gray lines are kind of colored particles that are indicating a flow line. And the flow line, and so those gray particles are sort of labeled here to kind of move over. And so you can see the way material flows. These, I guess, would be a flow tube of particles moving up and over the wing here. And you see they're moving pretty quickly here, whereas the particles moving under the wing are traveling relatively slowly. And if you look at the Bernoulli equation, the gravitational potential isn't very different between the top and the bottom of the wing. But what's happening is across the top of the wing, those particles have to move rather quickly here. So the v squared gets sort of forced up and over by the shape of this. And this isn't a consequence, this isn't a consequence of the fluid flow necessarily knowing anything about the top and the bottom. This is entirely set by local conditions, and the need for the fluid flow to maintain this laminar flow means that the particles have to move very quickly to get around this barrier here and maintain this sort of fluid, the sort of laminar flow with the stuff that's immediately above them and those with them above them. And because it has to be moving quickly here, this increases the v term in the Bernoulli equation. As a consequence, the p term has to reduce, and therefore the pressure gets lower relative to the bottom of the airfoil where things are moving relatively slowly. And this produces a net lift on the airplane, which is kind of cool. But there's two caveats that are important to know here. So the first caveat is that there's also a significant reaction force from the fluid striking the bottom of the wing. So what happens here, the fluid comes in, it bonks off the wing, and the stuff that travels along the bottom here gets a net momentum change pointed downward. So there is a net momentum on the wing that pushes upward. And that sort of forces the wing in the same direction that the lift happens. The other thing is that the laminar criterion doesn't mean that the time to travel across the top of the wing and the time to travel across the bottom of the wing are the same. If you watch the particles over time, it would take longer for a particle to go from this contact point here along the bottom of the wing than it takes for a particle that goes across the top of the wing to go all the way around to the end. So the layers are nice and laminar flow, but they do not come apart and come together on the wing at the same point here. This laminar flow is a criterion of how these particles right at the top of the airfoil relate to the stuff immediately above them, and that continuity of the flow there. Final caveat, not written in red here, is that this works really well as you're below the sound speed, but as you approach the sound speed, fluid becomes highly compressible, turbulent, and this type of flow becomes far more complicated for analysis. And if you look at the wings of supersonic capable aircraft, they actually have to rely more on this reaction force and change the shape of the airfoil relative to the this nice sort of lift model from the Bernoulli equation here. So it gives us a bit of how things go as we sort of change different regimes and how the Bernoulli equation breaks down. But it does give us some mechanism for sort of thinking about this in the context of the physics that we learn here in Phys 144. All right. That brings us to the end of fluid flow. We have some example videos coming up, but that kind of covers the sum total of the theory that we cover in the class. And I will look forward to discussing all of this in lecture with you. Have a good day.